5. So I'm going to continue the discussion of finite differences and actually show you how to solve boundary value problems. So I have a couple equations up here. So the first equation we want to solve, kind of our goal is we want to solve the boundary value equation d squared y of x dx squared is equal to 0. Now this is actually something you could trivially solve just analytically. If you integrate it twice, it's basically a straight line with the boundary conditions that x of minus 1 is equal to 1 and x of 1 is equal to 1. So even though this is a really simple equation, once we get the structure set up, then we can actually start solving boundary value problems that don't have actually even analytic solutions. And so the basic idea is we're going to take y of x and we're going to represent it as an array of points, right? So the points are going to be y at x of 0, x of 1, all the way to x of n minus 1. And these x's are going to be determined by a lin space from minus 1 to 1. And then previously in the lecture, I showed you that the second derivative of a function, right, is approximately equal to y at x plus delta minus 2y of x plus y of x minus delta all over delta squared. But the key thing is if we choose our x's, it's such that the distance between, say, adjacent points like x of 0 and x of 1 is equal to delta, and they're all equal distantly spaced, then we can just think about in terms of indices that d squared y of I at the ith position with respect to x is just y of I plus 1, right? That's the x plus delta minus 2y of x, which is your 2y of I. And then we're doing our I x minus delta, which in this case is going to be I minus 1 all over delta squared. So to illustrate this, let's just start out. Let's do 20 points. We're going to define our lin space. So x is lin space of minus 1 to 1 and then n. And then delta is just going to be, x of 1 minus x of 0. We could actually take any two adjacent points. And so we're going to do a function. So let's just do my fun. And then what we're going to take in is the values y. So that's basically what we're solving for, these unknown values of y that'll satisfy this equation. All right, so first we're just going to allocate our equation, right, array. So that's just going to be the same size of y, right? We have n unknowns, right? And so then we're going to have n equations, and then eventually we're going to return this equation. And so then we can do our equations. So the first one we're going to do is our boundary condition. So the leftmost point is minus 1, so that's going to be our boundary condition up there. And then we also have our right boundary condition as 1. So what we can say is x of 0, right, is just going to be simply that y of 0 is going to be equal to 1. So this is our left boundary condition. And then likewise, we have our right boundary condition. And this is going to take, we're going to take just the last point, equation of minus 1, and so we can say here y of minus 1 is equal to 1, or if you want to do it, we could do n minus 1 if you wanted to. Either way is legitimate. And then we just have to fill in our interior points. So for I in range, and this is like when we calculated the second derivative in the previous video, we can do from I from range of n minus 1, all right? So those are interior points. And then we're just going to use this equation. Basically, we're saying the second derivative is equal to 0. So we can just write that equation of I, right? And so what's the second derivative? Well, that's just going to be simply y of I plus 1 minus 2 times y of I, all plus y of I minus 1. And then we're going to set that, divide that by delta squared. And then we're going to set that equal to 0. Right, we don't actually need to put the 0 here, but I'm going to keep it there for when we change our equations. Then the rest of it is we're just guessing the value of y. So we're going to say sol is equal to root of my fun. And then we're just going to have a guess, and I'm just going to guess 1's the value 1. And then we're going to just say y is equal to sol.x. And let's make sure this runs. And then what we can do is do simply PLT plot of x comma y, and I'm going to do dashes like that, line width of 3, color is equal to red, and then PLT show. And so in this case, we're just going to get a straight line because our two boundary conditions are the same. And if you think about this as like a heat diffusion problem, this is like the steady state on a heat diffusion problem. But if I want to change, say, the right boundary condition to 2, right? So x of 1 is equal to 2. All I'm going to do is come down here and change this value to 2. And now I have a straight line between those solutions. So this is kind of a trivial example of solving a boundary value problem with finite differences. All right, let me grab this equation. So let's do a slightly more complicated equation. And so let me put this in here. And we'll do markdown. And so let's make this equal to 3 times y, right? So that's now the boundary value problem we're going to solve. Again, this you could solve analytically. You're going to get a bunch of exponentials, but as I'll show you, it's pretty trivial to just modify the code. So I'm actually just going to take this big block of code, come down here, and so if I look at my code, I have one boundary condition at 1, so that's my left boundary condition. I got the 1 there. I have my right boundary condition, which is 2 there. And then I have my equation. So before I set that the second derivative of y is equal to 0. Now I'm going to set it equal to 3 times y of I. So I'm going to have 3 times y of I. I should emphasize, just coming back up here, that again, this is the value y of x, right? So at that value of x is equal to 3 times the value of x. So this is the derivative at y of I. And the second derivative of y of I, which is basically this function here, and then we're just setting it equal to minus 3 times y of I. And then I can go ahead and run this, and now I get the analytic solution. So the right boundary condition is 2, the left boundary condition is 1, and we kind of have this kind of, basically it looks like a rope hanging between 2 points, and this would be kind of a reaction diffusion equation. So this would have an analytic solution. But we can modify it, so maybe we might want to put 5 in front of here, and let's make this y squared, right? So now we have an equation that doesn't have an analytic solution. So to make the modification, we just come down simply to this equation. So this part here is our second derivative. So if we want to take 5 times the second derivative, all we do is just put a 5 here times the multiplication. And then we have our 3 times y squared, and so I can just come over here and square that. I run it, and I get my solution. Again, 1 at the left boundary condition, 2 at the right boundary condition. And then once you get 20 going, you might want to look at a more accurate solution. So maybe we'll do 100 points, we run it, and we kind of have a little bit more accurate solution for it. You know, as n goes to infinity, this will gradually approach the analytic solution. So that's kind of just an overview of boundary value problems with fixed boundary conditions. What I mean by fixed boundary conditions is we're fixing the left boundary condition at -1 and the right boundary condition at 2. And then we just kind of write this equation, and all we're doing is replacing the second derivative with this basic expression for the second derivative. We can do the same if we had the first derivative. Typically, we're not going to see too many first derivatives in chemical engineering, but actually we'll do an example in a second, and then we do 3 times y of I squared. So let me do one more problem. So let me grab this and let me come back down here. So maybe we want to add another thing here. So let's just do dy of x dx, and I have no idea what this equation means, but I'm just adding a first derivative here, and let's see if we can solve this equation. Let me make sure I get, I have to make this markdown. And so I do my second equation. Now I have a first derivative operator here. And so all I'm going to do is just take the same code here, take this, and then I'm just going to add an expression for the first derivative. And let me zoom this down so we get a little bit more space. And if I have my first derivative, well, that's just simply y plus y of I plus 1 minus y of I. Right, that's the expression for the first derivative, and then we're going to divide it by delta, right? So again, this is the second derivative is right here, right? My first derivative is going to be right here, and then we're setting that equal to 3y squared of x, and so we have 3 times y squared of x. And let me see if this runs and I get a solution for that. Let's make sure this worked. So I'm just kind of coming up with an equation off the top of my head. And I got a true. So this would be the analytics or the numerical solution for this equation, which in all honesty, I have no idea how you would solve analytically. So this is one of these cases where you would actually want to solve the use a numerical solution for this. And again, the code is pretty straightforward. The key thing is just each point is that this is the left boundary condition at x is equal to -1. This is the right boundary condition at x is equal to 1. And then we're just setting that left point as 1, the right point as 2. And then we're just writing out our second derivative, our first derivative, and then the square term. So in the next video, which I'll probably post tomorrow, I'll cover like how to do no flux boundary conditions or derivative boundary conditions. It's only gonna add 2 lines to our basic code. Once we have the structure, it's all relatively straightforward to kind of calculate. Obviously, you probably want to do list comprehension with this rather than doing for loops, but I've done the for loops just to make it a little bit more explicit in what's happening with the different operations. All right, thank you. If you have questions, as always, please post them in the comment section or go to Piazza. Hopefully you'll find this useful. All right, thank you.